few of us have marked in the quiz, but the answer is saying increased disentanglement on increasing beta.
1 second.
Yeah, I have
Increase this
pasted.
angle.
Yeah, I have
They're
pasted
saying
the snippets.
Huh?
they're
I have
saying it
pasted
should
the.
be decreased disentanglement with reduced reconstruction quality.
Come again, Suhas?
Uh, it says it should actually, the correct option should be decreased disentanglement, right? But the option that is marked correct is increased disentanglement.
Yeah, it should be decreased. Wait, well, let's see. If beta is increased, what will happen is that the weight for the KL is increased. The weight for the KL is increased, then yeah, should be it should be both reconstruction quality and entanglement getting decreased. Okay. Okay. So Suhas, let us I think if the correct answer is marked as this thing, what is the correct answer given now? Increase disentanglement, reduce reconstruction quality, is it?
Yeah.
No, that is not correct.
Hmm.
Okay, so can we change this? Like, and
Yeah, I'll change the correct answer.
But sir,
in the
isn't it like whenever we are increasing the beta, it will be a stronger penalty on KL divergence, which is
correct?
promoting the disengagement
No, it
because
is
it's
not right.
representing.
No, see, because that's what I told you, right? The word disentanglement refers to having different posteriors for all x. I mean, for each
Correct.
x.
Right.
That is not happening, no? If you increase beta, the posterior collapse would be more, isn't it?
At the potential cost of.
Sir, when we are giving a higher value of beta, what we are
Hmm.
saying is that in the overall loss minimization, we have to minimize KL divergence loss more than we have to minimize reconstruction loss.
Correct.
So if we are increasing beta, eventually what we are doing is we are ensuring that KL divergence loss comes down further, which means
Correct.
disentanglement is going to increase.
Disentanglement is going to decrease. No, so if the KL is reduced further, that is what I'm saying. If the KL is, see, first understand that reduction of KL is inversely proportional to in disentanglement.
Right. So disentanglement should increase when KL divergence is reducing, right?
Correct. Yeah.
So then the marked answer is right. Increased disentanglement will reduce reconstruction
At
quality.
the
The KL
cost
is
of
increasing in the
accuracy,
process.
Yes, sir.
sir.
I think even multiple sources online say the same thing.
No, hold on. I
Higher
think
value.
I think I'm getting confused. Let's see.
There is a double
Sir, I've shared
negative
another
disentanglement.
image in
There's
the
a
chat.
hold on. Let me make it clear for myself, and then we'll discuss. Now beta is increasing. Beta is increasing, meaning KL is reduced further. If the KL is reduced further, then the disentanglement will decrease, right? Because disentanglement, KL is reducing further, the disentanglement has to reduce, correct?
So
Isn't it?
entanglement has to reduce.
No. KL reduction is entanglement reduction. See, suppose KL is 0. Okay. If KL is 0, then what happens? If KL is 0, the entanglement would be increased, right? Because all of them are collapsing to z given x. Sorry, normal 0, 1, isn't it? Isn't it?
Maybe,
Uh,
sir, we will come back with the proper way of this. So
I think
I
entanglement
believe
max.
whenever we increase the beta, it will increase the means at the cost of KL diversion. It will reduce the quality of reconstruction and increase the de-entanglement. But
Sir,
yeah, I need
ideally,
to read your notes again.
if
Hold
the
on.
disentanglement is reducing, it means for any input, the latent variable space is going to be almost similar. which means the reconstruction quality should be reducing.
Reconstruction quality reducing, that is definite. There is no
Right.
question
So
there.
basically,
The
we
question
cannot
is,
have a scenario where disentanglement reduces and reconstruction quality increases.
I mean, what do we mean by entanglement? So, for example, if the posterior becomes normal, has the entanglement increased or decreased?
So what my understanding is that entanglement being higher means that for any input image that we are giving, the latent space is coming out to be almost similar. That is why there is an entanglement in the latent space. For any input, it
correct.
is coming out to be similar.
That is correct. That is correct.
Right. So if we are saying that we are giving more weightage to the KL divergence, we are going to basically try to ensure that the entanglement reduces.
No,
We
when
want the
posterior
space to be
becomes
separated.
normal,
No,
when posterior
entanglement
becomes normal,
increases. More
yeah,
weightage to KL means
all of them will
entanglement.
become
Yes.
close to normal, right?
But
So
when
that
we
does
are
that
going
mean
KL is a
long?
loss. KL is a loss.
Mhm.
If we are
No, see, the thing is,
multiplying with
there
the
is a minimization operation happening. When we are giving more weightage to beta, we are going to further reduce the value of KL divergence, which means we are going to reduce the entanglement.
I mean, we
That is
all
what
agree
I
that
understood.
if the KL has decreased, then the posterior becomes normal, right? We all agree on that.
correct.
So
Yeah. So
posterior
does this mean entanglement has increased or decreased?
it's maximum entanglement, right? When your posterior has become a normal. That's what people are trying to say.
Yeah. So entanglement has increased, right?
Guys,
Yeah,
do you
So
see my screen?
entanglement
here
has
KL
Hold on, hold
loss
on.
function.
Hello. Hold on. Do you see my screen?
Yes, sir.
Yes.
Yes, sir.
Can you read whatever I have highlighted?
Yes.
Can you
Yes.
see what I have highlighted?
But what is good in this case? Bigger or smaller? Disentanglement is good.
This is an excerpt from the beta VAE paper. Okay, so higher the beta, better disentanglement.
Better means increasing, sir, right?
Correct. Higher the beta, increase disentanglement, isn't it?
But here they put minus of beta D, right, instead of plus beta. In the beta VAE loss term, they're subtracting instead of adding the loss.
Appropriate tune beta greater than 1 call. Hold on, let's see. Have they done that?
Yeah, the term above that image.
Yeah, there is a minus beta,
So
correct.
we did plus when we are discussing. So I think that might be the.
Oh. Okay, got it. So in our formulation, it was plus, is it?
Yeah,
Yes,
I
sir.
think so. Yes, sir.
It was plus beta.
But
Then it is.
how would plus beta work here? It wouldn't
No.
work, right? You need.
No. What I meant is, see, that then beta is taken to be negative, right? I
Oh,
think,
okay.
Suhas, let's do one thing. I think, there's confusion. So let us just ignore that question and just add 1 to everyone. That's all.
Okay,
Easiest
sure.
way to
Yeah.
deal with it.
Fine.
Yeah. But yeah, so I think you got the point, right? At least in terms of what is happening. If beta is taken to be a positive integer and the objective is written to be minus beta, then increase in beta, right, implies good disentanglement, right? Better disentanglement. I think that is what it is. Yeah, I think I'm convinced. Just think about it, huh? So let's move on because it's already pretty late. Okay. So Suhas, take a note of it, huh? We just have to add 1 to everyone in this particular quiz, huh?
Sure. Okay. Yeah.
Thank you, Suhas. I think you can leave now. If you want,
Okay.
I can start the class.
Okay.
Okay, thank you.
Sorry for
Yes.
interrupting. Can you please repeat what you said about the beta thing? Sorry.
See, beta, is a positive integer and the cost is KL minus beta, sorry, reconstruction minus beta. Okay.
Okay.
So if beta is increased, then disentanglement will become better because we are minimizing that KL. That's all. And beta is a positive number.
Okay.
Okay, so just
Fine.
read this beta VI paper. No, it's pretty well described there. I think that is correct. The only confusion was because in our formulation we took plus beta, and beta in our case was between 0 and -1. Right. So in that way, this question can be interpreted as if you put plus there, increasing beta means it is you're moving it away from -1. So, let's not get into that confusion. I think this it's the problem is with writing that as plus. That's all. So let us like ignore that question for everyone. Okay. So how many quizzes are done now? 4.
Yes, sir.
Sir,
4 are done. Okay. So we need 2 more. We can do streak. Let me just look at the calendar. 2nd, 9th, and 16th. We have 3 weeks, including today. So today is done. Shall we do a quiz on 9th and 16th? We can skip on 2nd because.
So 16th, I think you're planning for an online hybrid class, right?
Correct. We'll have a quiz then. No problem.
Okay.
We don't want. See, otherwise we can do it on 2nd and 9th also.
Sir,
that
second,
second, many people
Sir,
will
please
not
don't
be.
keep on second,
Hmm.
sir.
Okay. So then let us do it on 9th and 16th. Okay.
yes, thank you.
And assignments, we said 3 assignments, right?
Yes, sir.
Let me see.
I think you mentioned that you will give the third one in the November first week.
Coding assignments 3 into 15. So 2 is done. When is the deadline for your second assignment?
Yes,
28th.
28th.
28th. So then Sunday I will release the third so that we can finish by mid November. Okay, good. So one exam is done, quiz for 2 more quizzes and 1 more assignment. Okay, great. We are on track. Okay, so let us get back to classes. So you can see my screen. Can you see my screen?
Yes, sir.
Okay. Okay, so today's agenda is diffusion models, DDPM. Yeah, so I'll tell you rest of the course, the way I'm planning is we have 3 more classes, right? So I'd hopefully complete diffusion models today. Let's see. So today we'll do diffusion models and we'll have 3 more classes. And one class I will do noise contrastive estimation, self-supervised learning, these ideas. And we'll have 2 more classes. We can use it for autoregressive models and LLMs. Okay, that's how I'm planning. Okay, let's get back to stuff. So we were looking at denoising diffusion models. Just a quick recall. These are hierarchical VAEs, right, which have multiple latent spaces, capital T number of latent spaces. All the latent spaces have the same dimension as the data space. So you start from the data and keep projecting onto the latent space till it becomes uh, till the stage. I mean, till it becomes a Gaussian distribution. And from the latent space, you get back to the data space by traversing the path in the reverse direction. So the thing is, the dimensionality of all the latent spaces is same as that of the data space is something that we saw, right? And the It is not moving. Does somebody know why? Not able to move this.
Post kill restart.
Huh?
Post kill and restart.
What did you say?
You just restart the application, close it and restart.
Oh, still not moving. Okay, now it's moving. Okay, yeah. So the dimensionality of the latent space is same as that of the data space, something that we saw, right? The encoding process in the DDPM is not learnable. It's a fixed encoding process, and it's a Markov chain. Okay, that is one other thing that we saw. Okay, yeah. So we made the notation consistent with the literature. Data is represented using x naught, and the latent space is represented using x1 through x capital T. Okay. Um, yeah. So you start from x naught and go to x capital T, and the dimensionality of x naught is equal to xt for all t. And this is how the encoding process is defined. Okay. You have fixed alphas, alpha 1 to alpha t, and every xt is given by the previous previous latent, scaled previous latent plus some scaled noise, where you sample from normal 0, 1 and add it. Okay. This is the so-called forward process or the encoding process in a DDPM. It's a first order Markov process with Gaussian transitions. It means that you take one random variable, add Gaussian noise, you get the second random variable, and you traverse that Markov chain. Okay, and the stationary distribution of this Markov chain is normal 0, 1. And I hope that I also showed you that picture. Did I? Where you start from an image and get to the noise. I showed you that picture, right? Last class. Okay, great.
Yes.
Okay, so this is where we are. So let us move on from here. Okay, so I'll give you the high level idea of what we will do today, and then I will run through the math. Algebra is a little involved, but it's not difficult. Yeah, okay. Now the idea is, see, we have an encoding process. This is a fixed encoding process, okay, given by the following. So we have xt to be equal to root of alpha t times xt minus 1 plus root of 1 minus alpha t times epsilon, where epsilon comes from normal 0, 1, right? This is the encoding process, correct? So this implies that the conditional distribution of any xt given xt minus 1. What is this? Can somebody guess? We know that from reparameterization that if you start from a normal distribution, scale it and shift it with a certain mean and variance, you will still get a normal distribution, right? So these are normally distributed. So please note that my notation, normally distributed, the random variable is xt, correct? The mean is the root of alpha t into xt minus 1. Okay? The variance is 1 minus alpha t times identity. So there's a very slight abuse of notation here. I'll tell you what it means. See, when you're writing a conditional distribution like this, right? The condition random variable xt minus 1 is fixed in the sense that it has already taken some value. Okay, but the The random variable that is to be conditioned xt is not fixed. We have a distribution over it. That is what we have written, that it's a normal distribution over xt, okay, where the mean is square root of alpha t times xt minus 1. So this xt minus 1, which I have marked right in yellow, it is a fixed value because you're already in xt minus 1 and xt minus 1 has assumed a particular value. Okay. And given that xt minus 1 already has a particular value, you have an entire distribution over xt, which is given by that equation. Does it make sense? Why do you have a distribution over xt is because of this epsilon that is there. So you are given an xt minus 1, you get an entire distribution over xt. Is that all right to all of you? Okay, now what do we do is, as I said, we have an encoding distribution that is fixed. Now, please ask me questions if you have any, because I make it a little faster today because I want to complete DDPMs. Let's see. So we have, this is the encoding distribution. We have the decoding distribution, which is to be learned. Okay. What is the decoding distribution? We write that as p theta So decoding has to happen in the reverse direction, xt minus 1 given xt. So please note the commonalities between this and the VAE, right? In VAE, the encoding distribution is q of z given x, which is the posterior of latent given data. The encoding distribution is posterior of latent given data. Decoding distribution is posterior of data given latent. Okay, similar thing is happening here. I mean, here there is no one latent, no, there are directions of latent. So you start from x naught, which is the data, and you go to x capital T in one direction. That is the encoding distribution. The decoding distribution is in the reverse direction, correct? Now this has to be learned. Okay, so this is first of all, this is assumed to be a Gaussian distribution again. Okay, at xt minus 1. With a certain mean mu theta and a certain variance sigma theta. Okay, so this mu theta and sigma theta are the learnable model parameters. So this is what we will learn. These are the learnable model parameters. So given the fixed encoding distribution, okay, we will make a distributional assumption on the decoding distribution and we learn the parameters of it. That is what we are going to do. Now, how do we do it? So we learn that through same thing, ELBO optimization. We'll do the exact same ELBO optimization and we learn this. That's all. So rest is algebra. Okay, now you understood, right? So we have an fixed encoding distribution and we have a learnable decoding distribution. Given the encoding distribution, okay, we optimize the ELBO and learn the decoding parameters of the decoding distribution. That is what the idea is. Okay, any questions so far? Quickly, Sarvesh?
Sir, in the encoding process, where did the root come from? Previously, it was written alpha t xt minus 1 plus 1 minus alpha t epsilon.
Was it? Oh,
Yes.
sorry, my bad. It's my mistake. Or it's either here or there. Let me just see what the doesn't matter, right? I mean, depends on what your alpha is, but let's see what the literature does. Thank you for pointing that. This is just a second, huh? Give me a second. I think the problem, yeah, here I made a mistake. So this has to be, generally people write it as root of alpha. Okay. I wrote it correctly today, but yeah. Is that okay? That should clear it. Okay. Yeah, Abhitosh. Let's make it quick, guys. Yeah.
Why is the encoding process fixed here?
told you all that in the last class. Okay, because that is, see, that is how the DDPM is described. Okay, the encoding process is fixed because it's a, what do we want? We want a projection from the data space to the latent space. Okay, or rather Gaussian 0, 1. Now we do it in the hierarchical manner.
Yep.
Now, in a DDPM, it is a Markov chain, right? So you are doing a random walk through a Markov chain. Now, unlike in a VAE, where projection from the data distribution to the normal 0, 1, okay, cannot be guaranteed and has to be learned via that 5 encoder network. In a Markov chain, okay, if you have Gaussian transition, it can be guaranteed that the stationary distribution of a fixed Markov chain after sufficient number of steps converges to normal 0, 1. So, since you want your data to go to normal 0, 1 and you construct a Markov chain where there are slow transitions, you don't have to learn anything.
Yeah.
That's the idea. Okay.
Yeah,
I think I mentioned this in the last class, but anyway. Okay. Is this clear? So what we will do next is that under these model assumptions, we will write down the ELBO as usual and optimize it. That's all. So that's all the entire process is now. Okay. Now, just like with the case, as in the case of VAE, the final generation is via decoding. Because in VAE also you do the same thing, right? We will do the same thing here. The only thing is you have these kinds of model assumptions and we will have to optimize the ELBO now. Okay, let us do that. Let us start. Okay, so ELBO optimization for DDPM. Okay. Recall, you should recall that what was our ELBO? So log of p theta of x. Okay, we'll start from the definition of the latent variable model. That was integral. So log of integral p theta of x and z dc, correct? This is what it was. So finally, what was our ELBO? The function of theta and phi represented that as f theta of q phi. What was that? That was an expectation of log of p theta x and z divided by q of z given x. This was with respect to q of z given x. Do you recall this, all of you? Okay, we just have to write this down for a DDPM. Okay, that's all it is. Let us do that. So this is ELBO for DDPM or diffusion models TM is only a function of theta because there's no dependence on phi is equal to expectation of log of p theta. So what is x and z here? That is x naught, x1. Okay. Why is this? This is because x naught is the data variable and x1 through xt are the latent variables, correct? Divided by q of what is the latent variable here? x1, x2 up to xt conditioned on x naught. Okay, and we have that same q here, that entire thing. Can't write it. Is this all right? This is only a function of theta, as you can see, because encoding is fixed. Is this all right? Okay, so now we'll just shorten this down and write it as. So please pay a little more attention today because it's notationally heavy. It's not difficult, but if you miss one notation, it'll all be gone. I'll write this as x0 to t because I can't write 1 to t all the time. divided by q of x1 through t, which are the random variables conditioned on x0, and this is q. Is this okay? So every step you either react or interrupt me if you don't understand. Okay, otherwise it will be difficult for me. So this is all right? This is our elbow. So we'll have to optimize this with respect to theta. Correct? This is what we need to do. Correct? So let us do that. Just give me just a second. Yeah. Okay, great. So now this can be written as, I will not write this equal to every time. So let us write this expectation of log p theta x0 to t divided by q x1 to t given x0. Okay, this is what we want. Okay, so now this is okay. So first of all, what we should do is we'll have to write this as expectation of log of please observe here. So now p theta of x0 to t, I will write it as p xt, okay, times the product of t equal to 1 to t p theta xt minus 1 given xt divided by q product of t equal to 1 to t q xt given xt minus 1. Okay. Okay. Why did I write this? Now p theta of x0, x1 up to xt, okay, it is what we wrote as p theta of x0 to t. This is equal to p theta of xt, okay, times p theta of x.
எனக்கு அது டெலிவரி அட்ரஸ் அதான் வச்சிருக்கியா?
Get it the other way around. So that is p equal to 1, right? So p theta of x0 given
So I think it's p theta of x1 given x0. Right?
No. We are going in the reverse direction, no? Yeah. So
Okay.
I'm just writing the chain rule. Hold on. So this is no, should come on the other end, no? Hold on. Should be. So I've written it from the forward. I've written it from t equal to 1 to t. Should be the other end. So xt minus 1 given xt. Okay. So this is xt minus 2 given xt minus 1 and so on up to p theta of xt. Okay. Yeah, this is what it is. How is this? This is chain rule of probability, right? So now since the forward process is first order Markovian, right? Reverse process is also a first order Markovian process, which means that given xt, okay, xt minus 1 is independent of all the other states. That is why we have written it this way. Okay. Now this can be represented as p of xt into product of t equal to 1 to capital T p theta of xt minus 1 given xt. Now observe what did we do? We took off the dependency of theta on x capital T. Why is this? We have designed our xt, okay, because xt by construction is normal 0 1, isn't it? While transiting the forward chain, we have ensured that the capital T at x random variable is normal 0 1. Therefore, it is independent of p of xt is independent of theta. So this is p of xt. Okay, is it all right? So that is the numerator in that equation. So let us write down the denominator. So now what is q of, so what do we have in the denominator? We have q of x1 to t given x naught. This is what we have. What is this equal to? This is equal to q of x1 given x naught, q of x2 given x naught, and so on. The product of all this q of xt given xt minus 1. Sorry, this is x3 minus x1, x2 minus x1, and so on. Okay. Why is this the case?
Because they're independent of each other. Like the x1, x2 are independent distributions.
X1, x2 are not independent.
Okay, no, they are
This is the
not.
Markov process.
Exactly. This is the Markov process, right? This is the first order Markov process. This is because okay. See, this can actually be written as, you can write this as q of x1. Use the chain rule of probability, right? So you can write this as q of x1 given x naught, and you have q of x1 given, sorry, q of x2 given x1 and x naught into q of x3 given x1 or x2 x1 x naught, and so on, correct? This is by chain rule of probability, correct? So now q of x2, first order Markov and chain rule. Now all these terms, no, q of x2 given x1 and x naught, q of x3 given, so up to q of, should have written this and then written that. Okay, so this is q of x capital T given everything behind that, xt minus 1 up to x naught. Now, and since it is first order Markov, right? So it'll have I think you got it, right? I mean, this is what it is. Is that all right? Now I will perhaps take this and put it there. Okay. Yeah, Lokesh, yeah.
Sir, in the above equation, like p theta, is it going to xt or x0? Shouldn't it be going to x0 given x1?
Where?
Like you had mentioned p theta of xt minus 1 given xt times p theta of xt minus 2 given xt minus 1, so until p theta of x0 given x1, right?
So here, right, you have a p theta of xt term also at the outside. Okay, so what you said is correct. Hold on. See the way. Let us make it a little precise. So now here you have a this is equal to, you have a p of xt term here, okay? And the last term here would be obviously p theta of x naught given x. Correct?
Yeah, okay, thank you.
That's what I meant, yeah? Okay. Okay, so now please have a look at it. Now in the ELBO, right, we now have the numerator. Okay, so now the reason I did this is, how did we come from this step to this step? Okay, now there was the joint distribution of x0 to xt. Okay, under the model, we wrote that as this product. And in the denominator, there was the conditional distribution of latents given data, and we represented that using this product. Is that okay? Now I will continue from there. We'll take this equation. So now we have the ELBO to be equal to this. Log of expectation of log of pxt. Please note that I've taken the dependence on theta for the final random variable t equal to 1 to t. We have p theta of xt minus 1 given xt divided by product of t equal to 1 to capital T. We have q of xt given xt minus 1. Okay. I hope that all of you know how this equation came, right? This is what we showed. Okay. Now it's a lot of algebra. Let's keep doing this. See, I will omit the expectation term here. Okay. And only write the whatever is inside. Okay. So that it is easier. Otherwise, I'll have to write that bracket every time. I will write back the expectation term later. Okay. So omit the outer expectation. This is not any mathematical thing. No, this is simply to ease of writing. That's all. Huh? So don't think that this is some step or something. I'll write back the expectation later. So consider log of if whatever is inside. I will write that as log of pxt, okay, times. I will take back p theta of the first, or rather the last transition, okay, from the decoder. I will tell you why this was taken out. Huh? This will algebraically, this will turn out to be easier. T equal to T2 to capital T, you have p theta of xt minus 1 given xt, okay, divided by, we'll do the same thing with the encoder also. The q of x1 given x0, take that out, okay, and what is remaining is t equal to 2 to capital T q of xt given xt minus 1, okay. Right now, this log, I mean, this log is for everything. The log here. Okay. Now, this is, I'll use the law of logarithms and pull these things outside. P of xt times p theta of x naught given x1 divided by q of x1 given x naught. Okay. The second term is plus log of this one product t equal to 2 to capital T p theta xt minus 1 given xt divided by q of xt given xt minus 1. Okay, this should be all right. This is simply law of logarithms. Okay, now you consider what is important is the second term. Okay, so consider the denominator in the second term. Okay, so which is q of xt minus xt minus. This is the forward distribution that we know of, right? So now this can be written as q of xt given xt minus 1 and x naught. Can I write it this way? Now, why do I do that? This is because of algebraic convenience. So as we will see later, no, if we write this, then the ELBO, optimizing ELBO will become easier. There is one like vague interpretation that people have given in the original paper. I'll also mention that, but this is mostly because of algebraic convenience. Okay, please observe this carefully. This is one non-trivial step. Can we do this? Can we write q of xt given xt minus 1 as q of xt given xt minus 1 and x naught? Are these the same? Why?
Markov process is independent of the
This is because of the first order Markov property. If you condition it with anything else than the previous state, it is exactly the same. Okay. Now what we will do is we will use Bayes' law and write this as q of xt minus 1 given xt and x naught times q of xt given x naught divided by q of xt minus 1 given x naught. Okay, what is this? This is simply the Bayes law, right? I mean, you have probability of A given B and C can be written as probability of B given A and C times probability of B given C divided by probability of A given B. That is Bayes law with 3 variables. Is that okay? So this is Bayes law. Please with 3 random variables. You can please check that out in Wikipedia. Okay. Is that okay? This is simply Bayes law. So now note that the first distribution that you have, right, in the numerator, okay, what is this? I will write that down. So this q of xt minus 1 given xt and x naught. What is this distribution? Can somebody guess? This is the distribution of xt minus 1 given that the encoding process has started from x naught, okay, and landed at xt at t equal to t. Okay. See, please note that this is not the forward distribution, right? Forward distribution. What is forward distribution? Forward distribution is q of xt given xt minus 1. Okay. So this distribution is that while you are constructing the forward process, okay, what is the distribution of xt minus 1? How does the distribution of xt minus 1 looks given that you have started from x naught and landed at xt at t equal to t. Does it make sense? Do you understand what this distribution is? Basically, if you start from x naught, okay, depending upon what kind of noise that you add at or what kind of samples that you get for epsilon, xt can be very different, correct? Do you agree? Starting from x naught, you keep adding noise. Please focus on this and respond to me, okay, if you understand and not understand, because this is the key. You have to understand this. What I'm saying is you start from x naught, okay, and keep adding noise. Now, depending upon what sort of noise do you add, you end up at one particular xt. Okay, so every time you take the same x naught and add different kinds of noises, you get to different xt's. Do you agree with this? Now,
Yes, sir.
the question that we are asking is, given that you have started from x naught and landed at a particular xt, what is the distribution over xt minus 1? Does it make sense? See, note that this is not q of xt minus 1 given xt, because we are talking about independence between xt given xt minus 1 and the other thing, right? We are not talking about independence of, so xt minus 1 is not independent of xt or x naught given xt, correct? Markovian process says that xt is independent of everything else given xt minus 1. It is not saying that xt minus 1 is independent of xt. I'm just saying that it is in the reverse direction, and therefore this x naught cannot be removed. What did we do? Please note again. We had a q of xt given xt minus 1 term in one of the terms in the ELBO. Wrote that q of xt given xt minus 1 in terms of, just condition that xt minus 1 with x naught. That is okay because it's Markovian. Once we did that, we used Bayes' law to invert that, okay, and wrote this distribution in terms of q of xt minus 1 given xt and x naught, q of xt given x naught, q of xt minus 1 given x naught. And this distribution q of xt minus 1 given xt and x naught is simply the distribution of xt minus 1 given that the encoding process has started from x naught and landed at xt at t equal to t. Any questions here? The one question that might come up here is that why did we even write this as write this in terms of this q of this weird distribution, right? Is because, see, if you keep it q of xt given xt minus 1, okay, what you see is the numerator, okay, is going in one direction. Okay, theta decoding distribution is going in the reverse direction, and the denominator is going in the forward direction, correct? As it is. Okay, so if you want to optimize for the ELBO, you can't simultaneously do it from both the directions. So the idea is to represent the forward direction also somehow in terms of, introduce the reverse direction transition in the forward direction also. And that is why we use the Bayes law to invert it. Now, once you do this, what happens, you see, this q of xt minus 1 given xt and x naught is actually going in the reverse direction, correct? So that is the algebraic convenience that we wanted, and that's why we wrote it this way. Okay. Okay, so let us get back to ELBO now. So now getting back to ELBO.
Sir, one question.
Yeah.
If we do not if we do not have x naught, then also we could have come up with this Bayes rule, right? Like we just based on xt minus 1 and xt.
Your voice completely broke off. Was it only for me? I can't hear you at
Okay, let me repeat, sir.
all.
Am I audible? Hello?
Yes,
It
you
is
are.
Clear for us, Sanjit.
Sir, am I audible to you?
I can't hear you. Anybody else can tell me?
Yeah, we can hear him.
Yes, sir.
Sir, am I audible now?
Hello, can you hear me?
Yes, sir.
Someone is got disconnected. Just a second. Let me join back. Join. Just a minute. Oh, can you hear me?
Yes, sir.
Okay. So you were saying something. I mean, I completely missed it because I think some connection issues. Can you repeat what were you saying?
Yes, sir. Am I audible to you now?
Yes, yes. You are.
Okay. I'm saying if we did not include the x naught term, then also we could have come up with this like a backward distribution qxt minus 1 given xt.
No, you
Right?
can't. No, because how do you do that? See, then you will have marginals over. So you can use the Bayes law and simply write it as q of xt minus 1 times q of xt divided by q of xt minus 1, right? But you will have to find the marginals of you will get terms like q of xt, q of xt minus 1 and so on, right?
Correct.
These marginals are not computable.
Okay.
Okay. So, however, what we will see, we can compute both q of xt given x naught and q of xt minus 1 given x naught. We will see that in a while. Okay.
Okay.
Okay, great. So let us get back to ELBO. So what we were doing was we had log of pxt times p theta of x naught given x1 divided by x1 given x naught. This was the first term. Second term was plus log of product t equal to 2 to capital T. Numerator was p theta of xt minus 1 given xt divided by q of xt. It was given xt minus 1, right? Xt minus 1 and x naught. We just conditioned it on that. Okay. And let's use the Bayes law. If we use the Bayes law, then whatever we had written there, step 2. Copy this entire thing. Oh, could have better to write it down again. Okay, fine. Log of, thought I would save some time. This does not be x1 divided by q of x1 given x naught plus log of, okay, product equal to 2 to capital T. We have p theta of xt minus 1 given xt divided by, okay, we will use that Bayes theorem that we had written. This was q of xt minus 1 given xt and x naught times q of xt given x naught divided by q of xt minus 1 given x naught. Okay, so I will just show this to you. Have a look and let me know if it works. How did we do? We went from here to here, and that jump was done using the intermediate steps. Is that clear? Just have a look and let me know if it's clear. Okay,
Yes,
let us continue then. Again, copy this. Let me write this plus log of to capital T p theta of xt minus 1 given xt minus 1 given xt, okay, times the denominator of the denominator comes up q of xt minus 1 given x naught divided by q of xt minus 1 given xt and x naught times q of xt given x naught, correct? Now observe what happens to this product now. So this product f p theta of xt minus 1 given xt times, what is this product?
Q of xt minus 1 given x naught.
Divided by, hold on. So this is q of xt minus 1 given xt and x naught, okay, t equal to 2 to capital T. So this term into, we have terms like q of x to 2, right? So this is x1 given x naught into q of x2 given x naught and so on. In the denominator we have q of x2 given x naught, x3 given x naught and so on, right? So these terms will cancel out. Only two of the terms will survive. Can you see that? So what terms will survive? We will write this down now. Log of pxt into p theta of x naught given x1 divided by q of x1 given x naught, okay, plus log of, only two terms would survive. What are those terms? We'll have q of x1 given x naught. That is the first term that would survive in the numerator. In the denominator, we will have q of xt given x naught. Okay, everything else will cancel down. The other term that we have is plus log of product of t equal to 2 to capital T p theta of x t minus 1 given xt divided by q xt minus 1 given xt and x naught. All right. Is that okay? Everyone with me so far? Okay. So now look at this. No, there is q of x1 given x naught log of, you have log of ab by c. Okay. So this is log of ab minus log of c, and there is this term and this term gets cancelled away, right? That's why we took that x1 and x0 outside in the beginning. Okay. Now this will become log of a plus log of b. I can combine them and write that as log of p of xt, okay, times I will just trying to skip one step. That's why I was looking at it. Okay, let me skip it anyway. So log of p theta x0 given x1, okay, plus log of p xt divided by q xt given x0 plus sum of t equal to 2 to capital T log of p theta xt minus 1 given xt divided by q of xt minus 1 given xt and x0. All right, can you see that? Okay, we are almost done. 3 more steps. So note that there was an outer expectation, right? So bringing in the outer expectation. Okay, so what did we have? We had the expectation of, it was q of z given x, right? What is z? 1 to t given x naught. So this is our q of z given x. Okay, and this entire thing, this ELBO, which is whatever we wrote, no, log of p theta of x naught given x1 plus those 3 terms. I will not write it again. Okay, now what is to be noted is this will be equal to expectation of, okay, log of p theta of x naught given x1. Okay, this outer expectation now will be with respect to q of x1 given x naught. Why is this? See, while the outer expectation was with respect to q of x1 to t given x naught, since whatever the function that we have are only the functions of x0 and x1, the outer expectation will become function of x0 and x1. Is that okay? All right. Okay. Now, similarly to the second term, we'll come to the second term.
Sir, sorry, I missed to understand that part. Expectation of q of x1 to t x0 became
given x0 will become an expectation with respect to q of x1 given x0, because the term that you have inside the log, no, it is independent of all other random variables other than x0 and x1.
Okay. Yeah.
Right. Yeah. That is like law of expectations. Okay. Hold on. We have this conditional expectation argument which can be done. Okay, so hold on. Okay, so this is the first term. So the second term would be, we have the same thing, expectation of log of, what was that term? pxt divided by q of xt given x naught, and this expectation is with respect to q. Similar argument, we'll take xt and xt minus 1 given x naught. Everything else will be going away, correct?
Sir, why xt minus 1 here?
Q phi of, I think I made a mistake here while writing. See here. Oh, this was my mistake, sorry. So here, so q of x naught. Hold on. X1 given xt. Yeah, that should only be xt. Correct. This is only q of xt given x naught, correct? Yeah, this is what it is. Right. Now the third term plus is what dependencies do we have? Let us write it that way. Take the expectation inside the sum because it is linear 2 to t. Expectation of, we had log of
From x1 to xt minus 1.
P theta xt minus 1 given xt divided by q phi of, no, there is no q phi, sorry. It is q of xt minus 1 given xt and x naught, okay? And dependency is on q of xt minus 1 given xt given x naught, correct? This is fine, no? Should be all right. Okay. Now, one last step. We represent as xt minus 1 and x naught, right? This should be just thinking if I have to do it or give it as an exercise. Okay. See, what we should do is after this. Okay, let me write that down. This is equal to, let's write the first term. The first term is expectation of log of p theta of x naught given x1. Expectation is with respect to q of x1 given x naught. Okay. What is the second term? The second term is simply the KL divergence, no? KL divergence between q of t given x naught and pxt. This is by definition. Okay. And if you look at the third term is also can be written as t equal to 2 to capital T. There is an expectation with respect to q of xt given x naught, okay, times a KL divergence between q of xt minus 1 given xt and x naught, okay, and p theta of xt minus 1 given xt. Okay, so here is where the tricky part is. I'll tell you that. Okay, the first term and second term are okay, no? So the second term here, this thing is simply the KL divergence, right? By definition, that should be all right, correct?
Minus KL divergence, right?
Yes, of course, negative of KL divergence. So now what happened to the third term? That's tricky, right? So what we actually did is here to express this expectation, right? You have an expectation with respect to q of xt and xt minus 1 given x naught, correct? Okay, you can write this as product of two expectations. Okay, 1 over an expectation of q of xt given x naught, okay, times the expectation over q of, okay, I don't have space here. Let this by Pharma. Create some space and write it. Now we have expectation of something, right? With respect to, we have q of xt given, sorry, xt and xt minus 1 given x naught. Okay, now this can be written as product of two expectations. The first expectation is q of xt given x naught, okay, and the second expectation is with respect to q of xt minus 1 given xt and x naught. This is similar to Bayes rule, okay. This is called the property of conditional expectation. You either please take it as a homework or can ask TAs to do this. This is a like known result, okay. This is a simple, you can actually write this down. You can write this expectation with, you use the Bayes law and use the law of conditional expectations. This is called the law of conditional expectations. Okay, property of conditional expectations. Please have a look at it. Now, if I do this and write this expectation in terms of product of two expectations, okay, then what will happen? The outer expectation is still around. Whatever is the inner expectation, no, which is you will have an expectation of q xt minus 1 given xt and x naught log of p theta of xt minus 1 given xt divided by q of xt minus 1 given xt x naught. That is the negative of KL, isn't it, between these two distributions? Is that all right? Do you see how we got the third term? Any questions on this? Okay, so that's it. I mean, we have to now interpret this and compute this. So now what did we do so far is that ELBO for DDPM, so which is only a function of theta, we wrote that as expectation of log of p theta x naught given x1 with respect to q of x1 given x naught, okay, minus dkl q of xt given x naught and pxt minus this entire term. How do I paste this?
So I think if you long press on the screen and you might get an
So
option.
move to text and then paste.
What should I do?
Move to text T. Select T.
Select T.
Now you can paste.
I think you seem to be an expert in this. How do I move it now? Oh, I can't move it. painful, yes. Yeah. Okay, this is what we saw. So now this is all it is, and we are done. Look at the interesting structure now. If you look at the structure, what is the first term? The first term is very similar to the reconstruction term in BAE, right? X0 is your data, X1 is your first latent variable. You are reconstructing the data back using the first latent variable, that is the first term. Okay, and what is the second term? The second term is same as the prior matching term that we had in the BAE. Very similar to prior matching because xt. So look at this. No, this is like your q of z given x, right? And p of z. That's exactly how it is. First two terms are very similar to the VAE. But the other thing that is to be noted is this second term is completely independent of theta. There is no dependence on theta at all. So you can completely ignore that while training. Okay. What's interesting is the third term. This third term, right? I'm going to change it. This is called the consistency term, or they call it the denoising term or denoising matching term. Okay, so look at what is happening. Okay, so what is happening is that at every step t, okay, p theta of xt minus 1 given xt is telling you how should the model move to xt minus 1 given xt. That is what you need to learn. So this is the one that you should learn. Okay, so what is this term saying? This term is saying starting from x0, okay, and given the fact that you have reached xt, tell me what is the distribution of xt minus 1. So this is saying given xt, tell me what should be the distribution of xt minus 1. So now if you minimize the KL divergence between these two terms, intuitively what it will lead to is that if you traverse through p theta of xt minus 1 given xt, you would eventually get to distribution of x0, isn't it? Because what you are saying is this distribution Q is telling you that this is known. Okay, this is known. This is telling you that given that I've started from x0 and reached xt, what is the distribution on xt minus 1? This is telling me that given xt, how should I go to xt minus 1? So now if I match these two terms, this is actually matching denoising, right? This I can call it as matched denoising, and this is learnable denoising. Where we are whatever we know how to we know how to denoise, and we are matching that denoising with the learnable denoising so that we can generate data. And of course, from a hold on, I know this. From a mathematical standpoint, this works because finally what we are doing is minimizing the KL divergence between the model distribution and the data distribution via ELBO optimization. That is what we are doing. Okay. Now, what we will do next is we will take this consistency or denoising matching term and we will see how to compute it in practice. That is what we will do next. But I hope that you understood what these three terms are in DDPMs ELBO. Okay. Any questions here?
Sir,
Go on,
here how?
Yeah.
Sir, here how are we evaluating the non-denoising term? Like
that's the next thing that we will do. I told you, derived. Now we will see how to compute it. Non-denoising term has to be evaluated now. We will do it. That is what I'll do next. Okay. Yeah, Raghavendra, go on quickly.
Yes, sir. 2 steps above.
Can you make it quick, please?
Yes, I mean, how that the third sum, right? I mean, how did you change the expectation to xt and xt minus given x0?
That is because it's a similar argument. No, dependency is only on xt minus xt, xt minus 1 and x naught. Here, the expectation was q of x1 through t given x naught. Okay. See, dependence of whatever is inside is only on xt, xt minus 1 and x naught, isn't it? That's all.
But the log term, that the numerator term depends on xt minus 1 given xt. So
But the random variable, see, expectation, outer expectation is with respect to x1 to 3 to 1 to t given x naught, correct? Right. Now, what all terms we can drop in x1 to t is the question. We can only drop everything other than xt and xt minus 1. That's all.
Okay, so that given xt is also included when we compute expectation.
Isn't it? See, the distribution does not change. See, what changes is the dependency of whatever random variables are not there. You can just omit them from the distribution, joint distribution. It's actually writing this joint distribution, right, in terms of okay. So what actually is happening is, you see that we wrote it this way, no? Where was that? Yeah. So we wrote, this was the distribution with respect to which we need the expectation, isn't it? Okay, hold on, it is still coming up. Correct. This is the distribution with respect to which we need the expectation, and we wrote it as a product of so many things, right? Now, when you write it as a product of so many things, whatever distributions that are independent, you can just remove them and they are constants. That's all will happen. Okay. What will remain are the ones where the dependency is. So there will be q of xt given x naught and q of xt minus 1 given x naught. I've written that as q of xt comma xt minus 1 given x naught. That's all.
Okay. Yeah.
Makes sense now? Yeah.
Yep.
Okay. Okay. Anything else? So now what we will do next is that we will see how to compute this denoising, like known denoising term and learnable denoising term, and we will build a model. That is what we are going to do. Why is my screen stuck? Yeah, that is what we are going to do next, and that is how you train a DDPM, and we'll see how to sample from it. Okay. Shall we take a break? I think this is a good time to take a break. Okay. Shall we make it a shorter break, because people might have a hard stop at 12:15, 12:20. We'll make it a short break. So this is 11:07 in my clock. Let us get back at 11:15, huh? 11:20 or 11:15. What do you want? 11:20. Let's get back at 11:20. Okay. So please be exactly at 11:20. We'll continue from here. Okay. See you. Hello all, shall we continue? Shall we resume?
Yes, sir.
Okay. Okay. Let us look at the what to do is now to compute the consistency term. No? So it is simply the KL divergence between Q of xt minus 1 given xt and x naught and p theta of xt minus 1 given xt. Yeah, this is what the term is. Okay, first we need to consider somebody was asking no how to compute this, so let us see how to compute this. Okay, let us consider this. See how to do this. So this, let's use Bayes law. This q of xt given xt minus 1 and x naught to q of xt minus 1 given x naught divided by q of xt given x naught. This is Bayes law. Okay. What is this equal to? This is equal to q of is this all right?
Because of Markov process, right, sir?
Yeah, it's because of the Markov process. Xt given xt minus 1 and x naught is simply xt, correct? Q of xt given xt minus 1. Should be all right. Yeah. Okay. Now, so we know how to compute this. No, this we have. This we know what distribution it is. And we have to consider the distribution of q of xt given x naught is what we should do. We need this. Okay. How do we get this? Is the question. Actually, we can get this can be obtained using recursion. Show you how. We have. Okay. So what is this distribution by the way? This is distribution of tth latent variable given data, right? Yeah. How do we get this is the question. So we have xt to be equal to root of alpha t times xt minus 1 into, plus root of 1 minus alpha t times some epsilon, where epsilon comes from normal 0, 1. Okay, let me call this as some epsilon t minus 1. Okay, I mean, this is simply a sample from normal 0, 1. There is nothing sacrosanct about t minus 1, but let me write it that way just to differentiate it. I'll tell you. So this, now I can recurse over this. No, this is square root of alpha t, okay, into what is xt minus 1? Root of alpha t minus 1 times xt minus 2 plus root of 1 minus alpha t minus 1 times, we'll call this as an epsilon t minus 2 plus root of 1 minus alpha t times epsilon t minus 1. Is this all right? Okay, now this you can keep recursing this till you get x naught, but we'll have to see how one step of recursion happens, and then we can generalize it. Okay, now this is equal to, not of space to write this. This is equal to square root of alpha t into alpha t minus 1. Okay, xt minus 2, xt minus 2 that is the first term. The second term is plus root of alpha t minus alpha t times alpha t minus 1 into epsilon t minus 2 plus root of 1 minus alpha t times epsilon t minus 1. Correct? Okay, now what should be done is, yeah, okay. So consider these two terms. Okay, which is root of alpha t minus alpha t into alpha t minus 1 into epsilon t minus 2. So this we know is sampled from a Gaussian, okay, that has 0 mean, and variance to be equal to alpha t minus alpha t into alpha t minus 1 times I. Do you agree? Why is this the case? This is because, again, reparameterization, right? So you have a Gaussian, you have a scaled Gaussian. So epsilon t minus 2 is, I have to write this one, epsilon t minus 2 here is again normal 0, 1. Okay, if it's normal 0, 1, then something scaled with that will become another Gaussian with a different mean and a variance. Agreed? Okay, so this is one random variable, and we have another random variable here, which is root of 1 minus alpha t times epsilon t minus 1. This is again Gaussian. It's 0 mean. Variance is 1 minus alpha t times I. Is this okay? Okay. Now what we have under that different color. P1. This is not a good color. Okay. Now this term, oh, where did that color go? So now T, okay, corresponds to and therefore is another Gaussian random variable, because sum of two Gaussians are Gaussians, you know that, right? Gaussian random variable with the following properties. So now T is the Gaussian, okay, with 0 mean, okay, and the variance to be equal to 1 minus alpha t minus 1 times I. So you can please verify this, huh? Just take sum of two Gaussian random variables with these particular mean and variance and add them and see what happens to the variance. Okay, so this implies that I can write xt, okay, as root of alpha t into alpha t minus 1 to x minus 2 plus another random variable which is 1 minus alpha t minus 1 times some epsilon t minus 2, where epsilon t minus 2, already use epsilon t minus 2, let's call this as epsilon star t minus 2, which is Gaussian 0, 1. Okay, so you can simply see what I just did and take a minute and let me know if it works. So what did we do? Xt was given by the forward equation. Okay, just recurse over that. When you recurse over it, you will get a sum of two Gaussian random variables with different means and variances. Different variances, means are both 0. And we combine those two and reparameterize it into another Gaussian random variable. And we got that final equation. Is it all right? Any questions on this? Should be fine, no? It's easy. Yeah. So now I can do this again, go recursively. I can keep doing this. This implies that my xt, zoom it now. Implies that my xt can be written as root of alpha t minus 1 up to alpha 1, right? Alpha 1. Yeah, alpha 1 times x naught. Okay, plus root of 1 minus product of, oh no, I can write the product later. So 1 minus alpha t, same thing, alpha t minus 1 up to alpha 1 times epsilon, okay, which is equal to root of sum equal to 1 to t alpha I, okay, times x naught plus root of 1 minus equal to 1 to t alpha I times some epsilon. This is equal to root of alpha t bar times x naught plus root of 1 minus alpha t bar times epsilon, where root of alpha, or rather alpha t bar, is the product of all that. Alpha t bar is the product of all the alphas up to t. Okay. So now this is an equation. So now what does this actually mean? Okay, let me write it distribution and also then interpret where alpha is 0, normal 0, 1. So this implies that we have q of xt given x naught. What is this? What is this? This is equal to, this is a normal distribution again, because this, reparameterization. The distribution at xt, the mean is root of alpha t bar times x naught. Okay, and the variance is 1 minus alpha t bar times I. You note where did we come from? We wanted to compute the consistency term, and we had this known denoising term, and we used Bayes law to do that. So for that we wanted q of xt given x naught, and xt given x naught is computed recursively. See, this actually means that the tth latent sample, the tth latent sample is also tth noisy sample, no? In the forward, the encoding or the forward process can be obtained in one step. Okay. Without adding the noise t times. So this is actually because of recursion, that's all right. We used the ELBO recursion and found out that the tth latent variable in the forward diffusion process can be obtained in one step starting from x naught without having to hop the Markov chain for t steps. All right, this is okay. This is another consequence of having this first order Markov chain with recursion, right? We can do it that way. Yeah, Raghavendra.
So did we just prove that a Gaussian of Gaussian is also a Gaussian?
What do you mean by Gaussian of Gaussian?
Because I mean we are taking, so if you look at the steps, right? So x2 is obtained by taking a sample from a Gaussian, and then x3
Where
is
is
again.
x2? No, x2 is not from epsilon, is from Gaussian. No, x2 is not from Gaussian.
But if you see the forward Markov chain, I mean that's what we do, right? We take a Gaussian of the result and then again sample from another Gaussian.
I'm not getting what you're saying. See, xt is obtained by this equation, no? Where is another Gaussian here?
Yeah, but then it depends on, ultimately it depends on x naught, right?
Of course it does. So what is the question?
In between we are applying multiple Gaussians, right?
You're not applying any Gaussians, no? You take x naught and sample from a Gaussian distribution and add it to x naught. That's what we are doing.
Yeah, and we keep doing that.
There is no application of Gaussian. We are sampling from Gaussian, adding a Gaussian. Yeah, that we are doing. So,
I mean, does it mean that ultimately, see the last result that we get is again a Gaussian, right, with the different parameters?
What do you mean by last result?
So yeah, this
the
Q
distribution
of
of xt, correct, that is a Gaussian. So,
and the intermediate steps were also Gaussian. So
correct. So
with the different parameters. So my question
correct.
was, did we just say that if we keep taking Gaussian and then sample and then again take again keep sampling from a different Gaussians, the end result is the again sampling from a single Gaussian?
That is reparameterization. No.
Yeah. So that was my question. I mean, that was my point.
Okay. So it is not a question. I was expecting a question. So
it was not a question. It was just confirm whether my
understanding. Making an observation. Yes. Correct. Yeah. So now you can reparameterize any amount of Gaussian addition in terms of Gaussians. That's all it means. Yeah. Okay. Anything else? Okay. So now what did we do is we now know. Let's get back to this. Our goal was to get the consistency term estimated. No. So now we had this is the distribution that we had in the KL, right? So this is equal to this is by Bayes' law, okay? And then we use the Markovian property here. This is Q of xt given xt minus 1 times Q of xt minus 1 given x naught divided by Q of xt given x naught. Okay, this is what it was. Okay, now do we know the first term? We do. What is that? That is the definition of the forward process. No, it's Gaussian at xt, and we have root of alpha t times xt as the mean. Okay, the variance was 1 minus alpha t times I. So the variance. Correct. That was the first term. What about the second term? We just found that out, right? Here we found out what Q of xt given x naught was. That was another Gaussian with a certain mean and variance. Let us write that down. So this is Q of xt minus 1 given x naught. No, that is another Gaussian. Gaussian is at xt minus 1. That's the random variable. The mean is root of alpha t minus 1 bar times x naught. Okay, and the variance is 1 minus alpha t minus 1 bar times I. Comes from here. Okay, comes from whatever we just derived through recursion. And in the denominator we have another Gaussian.
Sir, sorry to interrupt.
Yeah.
The first term, it should be root of alpha t into xt minus 1.
Correct. Root of alpha t into x t minus 1, correct. Thank you for the correction. So this is xt root of alpha t bar times x naught. That's the mean, and the variance is 1 minus alpha t bar times I. Okay, this is what is the LHS? LHS is q of xt minus 1 given xt and x naught. This is what we called as the known denoising term, right? That's what it is. Okay, now look at this. See, this is if all the terms have things like this. Now you have e power minus some quadratic term. No, you have xt minus some mean time bar, or rather, it's all identity. So it will be like this. It will be xt minus some mean squared. Okay, times e power minus xt minus 1 minus some other mean squared divided by same thing e power minus and so on, right? Now, see, observe that the distribution that we have in the left side is a distribution on xt minus 1. Okay, what should we do now? Can somebody suggest what should we do now? And we know all these means, right? We know all these means and variances. What should we do now? So what to be done is e power minus xt minus 1 t minus 1 minus some mean. Okay. Express it this way. Okay. Now, how do we do that? This we do by what is called as completing the square. Does all of you know how to complete the square? What do you mean by completing the square? This means that suppose you have a term, a quadratic term like this, no, ax squared plus bx plus c. Okay, you can always add some, let's say, some d times x minus d times x. You can add and subtract things and write this in terms of, say, x minus some p squared plus some constant. You know this, no? This is called completing the square, right? So whatever expressions do we have inside the exponentiations, we need to complete the square in terms of xt minus 1. Okay, we'll get some mean and some variance. Is that all right? Can all of you see that? Let me show you the calculations. I will skip the calculations. You can simply go through that. I will just show you that. Do it later.
Sir, what about the xt term?
Xt term will become a constant, right? Because the LHS is conditioned on xt. So xt is given a particular xt, which is a constant as far as xt minus 1 is concerned. Okay.
Yes, sir.
Can you see my screen? Hello, can you see my screen? Do you see my screen?
Yes, sir.
Yes, sir.
This is what I'm talking about. See, we have these three Gaussians, right? There is one Gaussian for q xt given xt minus x naught. There is one Gaussian for the second distribution and one for the third. You have to write down all these Gaussian distributions and use the appropriate means and variances. And you should simply complete the square. This is the calculation that I'm skipping. See, it's only algebra. Okay, it's like high school level algebra. Please follow this. And I have given this paper to you. Okay, so please say this algebra. Finally, what will happen is this will become a Gaussian distribution. Okay, with a certain mean and a certain variance, because you have completed the square and you can look at this. No, this, all you have to do is rearrange the terms, add and subtract the terms such that it will assume a Gaussian distribution form, and you should read out the mean and variance. That's all we should do. Is that okay? So please follow that. I will skip this and only write the final mean and variance because it's simply an algebra. Did you understand, all of you? It's not complicated. Huh? You just have to run through the algebras. All right. Is it okay? You can go through it, and if you don't get it, you can always come back to me. I will tell you. It's not at all difficult. You will easily understand that. Share screen. Now this term will become so Q of xt minus 1 given xt and x naught now became a Gaussian distribution, right? E is a Gaussian distribution. Okay, distribution is at xt minus 1. The mean is, let's call that as mu q. Okay, and that will be a function of xt and x naught because these are conditioned on xt and x naught, and there will be some variance. Call it as some sigma q. This will only be a function of t or alpha t. It will be independent of this thing. I'll write down what these are. Where the mean of this distribution mu q, the function of xt and x naught, is given by root of alpha t into 1 minus t minus 1 to xt plus t into x naught divided by 1 minus alpha t bar. That's all. Now note that both of these terms, right? Both of these terms are known and computable, no? So now this means that this known denoising term can be computed. So we know alphas, we know xt, we know x naught, we know all of this. So that can be computed. So this is typically written as some sigma q squared times identity, where this entire thing is written as sigma q squared is a constant. Okay, that is what is done. Any questions so far? I think this is fine, no? Now what did we do? So we wanted that the third term in the ELBO was scale between xt minus 1 given xt and x naught, and we had p theta of xt minus 1 given xt. Okay, this is what we had. Okay, now in a DDPM, the decoding distribution, it's called decoding distribution or denoising distribution. It's also called the reverse process. This process is assumed to be a Gaussian. This implies we have p theta of xt minus 1 given xt. Okay, this is a Gaussian xt minus 1 with a mean mu theta. So this mu theta and the variance. The variance of this is assumed to be equal to constant. Constant which it is assumed to be equal to what the true thing is. So only the mean is estimated. Variance is assumed to be constant in the normal course. Okay, in the literature, variance is assumed to be a constant. Okay. Okay. Now what happened is that because it's Gaussian, so we have the scale divergence between q xt minus 1 given xt and x naught, okay, and e theta of xt minus 1 given xt is now a scale divergence between the Gaussian parameterized at mu q and sigma q, and this is a Gaussian that is parameterized as mu theta and sigma q. Is this all right? Now, scale between two Gaussian distributions is known to be, it can be analytically computed. It is given by half log determinant of sigma q minus d, where d is the data dimensionality, plus trace of sigma q inverse sigma q plus mu theta minus mu q transpose, the quadratic form sigma q inverse mu theta minus mu q. Okay, you can just take this as a homework and do it. Show that the Gaussian distribution between two, scale divergence between two Gaussian distributions can be computed this way. This is equal to half. This is log 1, which is 0. So, okay, let me write it. Log 1 minus d. Trace of inverse of sigma q inverse times sigma is also equal to d. That can be shown because it's just constant times identity, d dimensions, it will just add up to be d. Trace is the sum of the diagonal elements if it's a diagonal matrix. Plus, so this log 1 will go away, these two d will go away. Sigma q inverse is a, so you have mu theta minus mu q transpose. Okay, so this is small sigma q squared I. This is what we have written that as. This is mu theta minus mu q. Okay, that's all. So this will be equal to half. There's an inverse here. Okay, so it will be 2 sigma q squared times the norm of mu theta minus mu q whole square. This is actually the elegance and beauty of DDPM, that after doing all that, the final denoising matching term will simply be a mean squared error between two means. Okay, that's all. Actually, we are done. There is the rest of the things that we do is only some reparameterizations, and we'll see how to implement this using a neural network in a while. Any questions here? Yeah, Sanchit.
Sir, why are we assuming that the decoding distribution is Gaussian? And like in
That
a
is
general sense,
because I'll tell you. That is because, see, we are not assuming the distribution of data to be Gaussian. We are only assuming the conditional of the latent given another latent to be Gaussian. Okay, that is one thing. Why are we doing that assumption is that what can be shown is if you have a forward Markov chain, okay, with Gaussian transitions, there exists a real reverse Markov chain that also has Gaussian transitions is something that can be shown. Okay, but what changes is the parameters. What changes is the parameters. So one is mu theta, the other is some other parameter. No, so but what can be shown is that if you have a Markov chain whose forward distribution is Gaussian, transitions are Gaussians, okay, then the backward distribution is also Gaussian with a different parameters.
so like in VAE also, we try to assume like what I'm trying to
The
understand
decoding
is.
distribution.
Sorry, sir, please continue. So like for VAE also, we were trying to assume that the latent space will be a Gaussian distribution, like a normal distribution, and here so like why are we so much biased towards a Gaussian distribution in almost all of the models?
No. See, that is a design choice. You can see while in a naive VAE, we assumed it to be Gaussian, but in all VQ VAE and the other vampire, etc., it can be modeled as something else, right? Similarly, see, but here what you should see is that the stationary distribution here, which is the distribution of the Tth latent is assumed to be Gaussian. We are not assuming the intermediate distribution to be Gaussian, but only the conditionals are assumed to be Gaussian, which is okay. So, I mean, yeah, why are we assuming it to be Gaussian is because like it's an isotopic distribution, right? I mean, it is a distribution that has infinite support, so it is easy to work with. There are diffusion models where they have used another, other exponential family of distributions, but they lead to a similar thing because see, note that nowhere we are assuming that P of x naught is Gaussian. This is not Gaussian at all, right? So P theta of x naught, which is our data distribution, is actually given by the product of all those distributions, right? We know that we use the chain rule and do it. So the conditionals are assumed to be Gaussian, which is okay. You can have conditional to be Gaussians and you can use the Gaussian conditionals to model any distribution of interest. Okay. So that way, I mean, if your question is that isn't Gaussianity assumption restrictive here, it is not restrictive at all. It can model any distribution, only the conditionals are assumed to be Gaussian. Now, why are we doing that choice in the reverse process of DDPM is because what can be shown is that if you construct a Markov chain with Gaussian transitions in the forward direction, the reverse transition also happens to be Gaussian, okay, with different set of parameters is a known result. Is it all right?
Okay,
sir. The reverse process is not deterministic, or?
It is not, no, we are finding out mu theta here. It is parameterized by mu theta. We will find that out, no? See, now finally what we are finding out is this mu theta. Mu theta is something that we find out.
But that cannot be arrived at analytically, or?
No. That is our model, right? That is the whole point. If you look at
the forward
the
process
model
that we said is fixed.
is known.
Yeah.
Of course, it is fixed. You see this? You see this? P theta, mu theta, and sigma theta are learnable. But in practice, what they do is they make sigma theta a fixed thing. Only mu theta is learned. That is our model. See, if you make the reverse process also fixed, then what are you learning?
Yeah, understood.
Hmm?
Yeah, understood, sir.
Yeah. Is this okay? So finally, it all boils down to, I think I'm doing a multi-scale thing here, right? One thing is at some scale, the other is other scale. You look at this. I think I zoom it inadvertently somewhere, it'll become that should not be an issue for when you go back and look into it. I think you can also zoom out and zoom in and look into that in different scales, I suppose, right?
Yes, sir,
Yes.
but we can't take printouts. So it's okay.
Oh,
But
because
that's
of the
okay,
scale
sir.
issue. Because
Yeah,
of the
it's
scale
okay.
issue. I see. Okay.
Don't do that.
So
much
had it
printing.
come again?
We don't print that much, but if sometimes we like to take a printout, then
Okay. So I
taking a
think
form PDF, yeah, it's
the
okay.
positive side of it is, I'm helping environment, so it's fine. Yeah.
Yeah.
Okay. So is this all right? So what happened is that finally this ELBO thing boiled down to there was this term, this that's all, right? You'll have to minimize this. So of course there is that another term, no, this was minus scale. There was this term of expectation of log of e theta of x one given x naught. This was also one term. That's all, right? So these are the two last terms that is there in the ELBO. So we'll have to now implement these two things using neural networks. Okay, and then we'll estimate these two terms, minimize them, and then learn how to sample from it. See, those two things have to be done. I need at least half an hour to do that. Shall we stop here? Because it will be nice if I do it in one stretch. I'll do it in the next class. So the only problem is I wanted to do that today because I was planning to give your assignments out on like Sunday, which is tomorrow. Okay, maybe I'll quickly tell you how to do that so that you can like start looking at your data, building these things. Okay, shall I take 10 more minutes? Okay, so that at least you know how to train this. Okay, right. Now let's do this reparameterization. We can actually implement it this way, but people generally implement it in a different reparameterization. Let us do that. We have reparameterizing.
Sir, there will be the KL divergence term also, right? Third one.
No, that is the third one is what we showed as this
No,
difference
sorry.
between the means. Second one.
Yeah.
That is independent of theta, no? We ignore that. Yeah.
So, sir, what will be its use for? Like which term, which component will it be used for updating in the DDPM?
What? I didn't get the question. Which term? What will be used for?
Sir, the KL divergence term that was independent of theta. Are we saying that we won't be using it anywhere for updating?
Yeah, because model training, of course, no, it is independent. There is no model at all. There is no dependence on model. It is a constant as far as the model is concerned.
Okay.
This comes because of the fixed forward process, right? And also Yeah, this primarily comes from fixed forward process. Okay, so I will maybe quickly tell you what this is and hand wave and do the maths the next time. Okay, so that you can start implementing. See, what's the idea is you have this term, no? You have mu theta minus mu q as your loss. Okay. Now what is done is we have this mu q as, what is mu q? Some constant c1 times xt. I had written that. Some other constant times x naught divided by some constant, right? Or rather, I can write it as some linear combination of x1 and x naught. This is how mu q was, correct? Now we have xt to be equal to, we used that recursion and showed that xt was equal to root of alpha t times x naught, okay? X naught. So please pay attention here because this is what I'll ask you to implement, okay? This is x naught plus root of 1 minus alpha t bar times epsilon. This is how it was, correct? Now, if I rearrange these terms, I can write x naught in terms of xt minus root of 1 minus alpha t bar times epsilon divided by root of alpha t bar, okay? This implies that my mu q now can be written, okay, in terms of, I can get rid of x naught, right? I can write this as some other constant k1 times xt, okay, minus or plus some other constant times epsilon. Do you agree? All of you agree on this? Hello? Am I there? Audible? Yeah. Okay. So this is all it is. So this implies that I have my mu theta, right? Mu theta, which is a function of xt. I can also write this as, okay, some constant k1 times xt plus, okay, k2 times some epsilon theta, okay, which is a function of xt and t. So what am I saying is the following. Now, see, mu theta was the mean of a Gaussian random variable, correct? Okay, right? I can always reparameterize that in terms of some other constant xt, isn't it? Do you see what that means? This is reparameterization. Do you get the idea? The idea is that mu theta was the mean of a Gaussian random variable, okay? I can always reparameterize that in terms of some other constant xt, isn't it? I just have to arrange these k1 and k2 terms. So I've just simply reparameterize them. Okay. Okay. And theta, right? That would get designated into this epsilon theta. Basically, what I've done is I've written this mu theta in terms of some epsilon theta and constant times xt. Is that okay? Okay. So now this implies that my loss that I had, no, mu theta minus mu q, now becomes proportional to epsilon minus epsilon theta. Correct? Isn't it? Because those constants will get cancelled away, no? We have like reparameterized mu theta also in terms of the same constant as that of mu q. So those constants xt gets cancelled away. So it will only be in terms of epsilon and epsilon theta cap. Is this clear to all of you? Hello? Okay, so now how do you implement this in practices? That you have a, so please note that the dimensionality of And I will do it like more thoroughly in the next classes, just to ensure that you will get started with your assignment. Okay, you will have a neural network. Okay, theta neural network. This will have this kind of architecture is called the U-net architecture, where the dimensions will keep on decreasing, hit a bottleneck, and the dimensions will again keep increasing. Okay, this is because the size of noise here epsilon is same as that of the input. Okay, so now what does it take as input? It will take input xt and t. Okay, and this will predict epsilon theta. That is all. That is all the training of DDPMs. The last function is epsilon minus epsilon theta cap xt comma t. Okay. Now what is xt? Xt is, as we know, a root of alpha t bar x naught plus 1 minus alpha t bar times epsilon. That's all. This is how you train. How do you do it? Take an x naught, okay, and compute. So take x naught, sample epsilon from normal 0, 1. Okay. Compute xt using this equation. Okay. So give that xt as an input to the neural network. And whatever the output is, match that output with the epsilon noise that you have added. That's all the DDPM training is. Then you backpropagate. And you do it for multiple t's. You're minimizing the elbow. Is this clear? See, I mean, okay, I will not take any questions now because it's 12:20. We will start from this the next class. Okay, I will tell you like precisely what the architecture is and how do you do this, what the loss function is and all that. But this is all it is, right? So basically what's happening is, given a data point, you add some noise to it, okay, and you get the tth latent variable, pass that through a neural network and try to predict what was the amount of noise that was added to get this xt from x0. That's all it is. Clear?
So we pass it only once or repeatedly for the same data point?
Do it in batch, no? Do it for different t's. You take all data points. So we did all analysis for one data point. You do it for all data points basically. So for one data point, you'll have to sample multiple t's because you have a sum over all t's here, no? T equal to 2 to capital T. Take multiple t's for a given data point, train the neural network, and do it for all data points. That would be one epoch. Try it for multiple epochs. That's all.
Yeah.
Yeah. This is how you train a DDPM.
So, sir,
How do you?
Multiple t's per data point, and we have to take batches of such data points.
Of course, no, because you need to train it through the entire data set. Yeah, we'll do this. We'll do this more thoroughly in the next class. Now, half of the next class will be on like training diffusion models, and I'll tell you how these are related to what are called as core-based models. And then I'll talk about the conditional diffusion models, where all these stable diffusion, imagine Dolly, etc. They will take a text and generate the corresponding image, right? How do you condition these models on text is something that I'll tell you. That would end the diffusion models, right? Half of the next class perhaps. And the other half, we will do autoregressive models. We'll start with these language models, okay, in the next class. Okay then, that's it. See, I rushed through this implementation because I will give the assignment tomorrow so that you can, if anyone wants to start doing it, you can start doing it, get your data loaders and write the equation for this noisy one, get the network and start training at least. No? So by the time next week, we will thoroughly complete it so that you can implement it completely. Yeah.
So where can we
By the
find
way,
the reference to the papers?
In my handwritten notes.
Okay.
Handwritten notes. It's always that. I mean, like my handwritten notes is pretty comprehensive. No? It will have everything. Okay. Okay,
Sir,
then, that's it for today. Yeah.
Sir, one question, like not what this related. Sir, why can't we have quiz on the end of the class or in between? I mean, it's very difficult. I mean, we have like, I have like Friday late night meetings with the US counterparts. And because of that, sometimes it gets very late, the 9:20
Oh,
threshold.
okay, no problem. We'll do it after
I mean,
the class. No?
I am taking the quiz post 9:20. So that's why I just, I am taking the quiz first and then joining the meeting, like the class. So just in case.
Okay,
I mean,
okay,
if
okay.
possible.
2 more classes, 2 more quizzes. We'll do it after the class. No problem. Okay.
Sure, sure. Thank you so much.
Okay then, huh? So have a nice weekend. Happy Diwali to all of you. We will meet on 2nd, no? Next week. Next Saturday, we'll continue with this. Okay.
Sir,
Thank
one
you.
Thank you, sir. Happy Diwali.
Thank you, sir, and happy Diwali.
Happy Diwali.
Bye bye. Yeah.
Thank you, sir.